Okay, so when you're trying to do the Hungarian algorithm, basically what it does is it works out how to allocate a task to an individual employee, or it can be allocating preferences or anything. So we can't have any individual task be skipped, and we also can't have any individual person doing all of the tasks or doubling up. So what that means is that we need to make sure that we allocate a task to each individual person that they are going to be the best alternative at. So the Hungarian algorithm basically goes through all the different possibilities without us actually having to consider every single one of them. We can just work through the steps. So the first thing that we do, the textbook does do it in a bit of a confusing way. You can speed it up a little bit by not doing the covering the zeros with a minimum number of lines every single step of the way. You'll usually find you need to subtract from the rows and the columns first before you'll even be close to allocating. So we can cut it down like this. So the first thing is we want to identify what is our minimum number in each of the rows. And this is going to work out who, in this case, for say operator A, person A, this works out what they're best at, which machine in this case they're going to be fastest at, if these are all the times that they take to complete using those machines. So we can see their best machine, their minimum number is just here at machine Y. Person B, they're going to be best at Z. Person C, they're going to be best at Y as well. So we've got a tie, and this is where the Hungarian algorithm will come in handy. And then with D, person W here, machine W is going to be what they're going to be best at using. So we can kind of see that we could probably already allocate machine W to person D. We could probably allocate machine Z to person B. But the problem then becomes, how do we allocate machine Y and who gets machine X, since no one seems to be best at using that machine? What you've also got to factor in is that even though there's a tie between A and C, there may be a better alternative in also giving, say, machine Z to person B, because perhaps the alternative for persons A or C might actually be better if they were to be given Z. Doesn't look like that's the case in this one, but never make any assumptions. If you can't allocate immediately, follow the entire algorithm. So the first thing we do is what I would just call row reduction. So we're just going to subtract the minimums from each row. So you can see here we want to subtract 26, here we want to subtract 26, subtract 23, and subtract 20, and we'll put our answers down here. So if we subtract 26 from each of these, we'll get 12 in this position, then we will get 9 in this position. We should get a 0 every time wherever the minimum occurred, 26 minus 26, and then 54 take away 26 is going to be 28. And then we can keep going. So now we take 26 from all of these numbers, we get 6, 26 take away 26 is going to be, 9 take away 26, 32 take away 26, 6 again, and 26 take away 26, there's our 0. Taking away 23, so then we'll have 21, then 3, there's our 0, 35 take away 23 is then going to be 12. And then finally take away 20 from everything, so 0, 6, then 12, and 9. And so what this does is it now shows you the excess number of minutes that each person would take on each machine if you weren't to give them their preferenced machine. And so the idea is we're constantly looking for the minimum number and for zeros, because zeros represent the best possible allocation. So then this is where the textbook would say to do the thing where you cover it with lines. We're not going to do that. We're just going to go straight into a column reduction to save ourselves a step. And we can see that anywhere where there's columns of zeros, you're just going to be subtracting 0. So let's circle that. They're clearly going to be the minimums. And you don't really have to circle all the zeros. But this one here, the minimum now is 3, and there's a tie. So we're going to now subtract 0 from here, so take 3 from this column, take 0 from this column, and take 0 from that column. So all the ones with zeros, they're really just going to be copying them in, so we may as well just get that out of the way. 6, 21, and 0. And then here we're going to take away 3 from everything, so that'll give us 9 take away 3, 6. We'll have a couple of zeros along here, and then 3. And again, all of this will be copied in because we're just subtracting 0 in this case. And this will happen a lot. Saves you a little bit of effort. And there we go, there's our column reduction. So the next thing that we're going to do is we're now going to try and cover the zeros with the minimum number of lines. So wherever you see rows or columns of zeros, 2 or more, then generally that indicates to put a line that way. So I can see, for example, a couple of zeros going this way. I can see 2 in that one there. I could have gone this way as well, but it probably won't make a difference. And then here, I'll do 1 that way. It doesn't matter whether I do row or column to cover that 0, and this one as well. And so now, what this means is technically when you can cover all the zeros in the minimum number of lines, where that number of lines is equal to the number of allocations you have to make, 4, then technically it actually does mean that you can already allocate. So we may not have to go to this next step, but I'll go through it anyway, and I'll come back to this here. So what we would then do is look at what is the minimum uncovered number. And in this case, the minimum number that is not covered by a line is going to be 3, like this. So let's circle that. And what you do in the next set is you're going to add 3 to all of the crosshairs, the ones that are covered twice, and then you're going to subtract 3 from all of the uncovered numbers. All the ones that are covered by a single line, they're just going to be copied in, right? The idea is that those are often going to be your zeros. You want to keep an autosave of who was the best option in each particular case. So if we add 3, I like to do it by position. If we add 3 to those 4 spots that are in those crosshairs, we can see we get 6 plus 3 is going to be 9. 21 plus 3 is 24. And then over here in column Y, we have 9 and then 3. Like that. Let's also then copy in all of the covered numbers because they're not going to change. So 12, 0, we have a 0 here and a 0 here. And then we have a 12, a 0, a 0 and a 12. Seems to be a lot of the same number. And then we're going to subtract 3 from all of these uncovered numbers. So we're going to get a 0 where that 3 was. Then we're going to have 3 here, 6 here, and 25 here. And then what you would do is try to cover all the zeros again with a minimum number of lines. And if it still didn't work, you basically just reroute back to the minimum row subtraction, but you would use your updated numbers, basically. It's very rare for that to happen, so it often doesn't occur. So if we now, I'll switch colors here, I might go to green. And so if we try to cover all of them, we've got 3 zeros here, so I might go for that one. Switch to a straight line. Then I can cover like this one here, and then I've got a couple of zeros there, and another one there, and you can see again, I've been able to cover all the zeros, and the minimum number of lines it took to do that was still 4, so it tells me I'm ready to allocate. Technically, I was ready to allocate over here. And so what that means is, if we get rid of some of those lines now, normally you'd have those drawn in, we would allocate based on the zeros. So I like to go for the fussiest jobs and people first. So if you look down each of the columns, if there are any columns where there's only 1 0, then circle that 0. So we've got only one person, D, is best at using machine W. There's only one person that's best at machine Y here. There's one person that's best at machine Z, and that already does the allocation. You may also find certain rows have only 1 0. So in this case, there it is there. And that then has got your allocation for you nice and easy. So that means that person A should go to machine Y. We'll do like a bipartite graph here as well, A, B, C, D, and then actually I'll do that a little bit differently. Let's put it in order. W, X, Y, Z. So person A should go to machine Y, then person B should be allocated to machine Z, person C allocated to machine X, and person D allocated to W, like that. But we can also prove, we can come back over here for a moment, and we can see that if I just kind of roughly get rid of some of these, don't know if that's going to work very well, like that is going to have to do, I think. So we can see that the zeros we might go for rows here. There's definitely a 0, only 1 0 in that row. There's only 1 0 in this row as well. There's only 1 0 in this column. And therefore by default, even though there's 2 zeros and 2 zeros here, there's only one option left for C. they must have been better at a lot more tasks, which means that they're a little bit less picky on who we allocate them to, and we end up with the exact same allocation, right? And so really what that proves is that if you go down the algorithm too far, it won't make a difference. Ideally, you want to find when you can allocate as soon as possible, and that is when the number of lines is equal to the number of allocations. That is the minimum number of lines that it takes. As soon as you can do that, then you're free to allocate. The textbook says that you can do that at every single stage, and that is technically true, but you'll often find you won't be able to allocate until you've at least done the row and column reduction. So there's really no point in checking here and here, because it's very, very unlikely to ever be the case. And it doesn't take all that long to fill it in anyway. So even if that was the case, then it means that you can just answer every question in the same style. You don't have to kind of adapt to different questions. You can just take that same strategy every single time. There we go. So that's the Hungarian algorithm. We just do minimum row reduction, column reduction, and we check with our lines. We can allocate minimum number of lines to cover all the zeros. If the number of lines is equal to the number of allocations, we allocate from there, looking for the restrictive rows and columns with only 1 0 in them to start off. If we can't, if it takes 5 lines or 3 lines to cover all the zeros, and we need 4, then it means that we need to keep going, and that's where we add the minimum uncovered number to all the crosshairs, subtract it from all the uncovered numbers, and then reallocate from there. So then you try the lines again. If that doesn't work, go all the way back to row reduction, start the process again.